Today's topic, okay, about chapter 7, notches and weirs. So, so the objective of this chapter is to acquire fundamental concept of notches and weirs. So at the end of this chapter, students should be able, one is derive equation to calculate discharge Q or flows through rectangular and V-notch weir with an aid of diagram. So you may understand about the flow flow over notches and weirs. So then from that figures, you may derive the equation for both of these types of weirs. And then after that, after end of this chapter, you can sketch and label appropriate diagram based on the question. And then number 3, apply appropriate equations to analyze fluid flow characteristics over notch and weir. And then the last one is calculate parameters with height CD or theta of the notch by using appropriate diagrams. So it is based on the question given. If the question asks us to find what is the width of the notches for the rectangular notches or for the V-notch notches, then you can use appropriate equation and then rearrange the equation to find what is the objective of this of your questions. Okay. Then what is actually notch and weirs? Notch is an opening in the side of measuring tank or reservoir extending above the free surface. It is, in effect, a large orifice which has no upper edge, so that there is a variable area depending upon the level of the free surfaces. So this is the figures shows. This is schematic diagrams shows what is actually notches. So when there is a flow here, we have so if we have a flow, then we block that flows. So this is the free the flows stream, and then we block the stream with notch, and then that flows over this notch, and it is at this side we have an opening side. Either it is a rectangular notches where this the shape of that opening is in rectangular, or we have V notches where the opening of that notches is in V shapes. So what about the weir? Weir is on the large scale. If you go to the lab, then the lab scale is the notch, and when you go for the large scale, we call it as a weir. So for example, to measure a flow of river or maybe sharp edge or have a substantial breadth in the directions of flows. So you may found the weir for a dam. So normally dam will use ampangan will use weir in their opening to flow the waters from the dam to the river. Or maybe you want to calculate or you want to measure the flow rates of the water in the river. Okay, that is the differentiation between notch and weirs. Notch is for the lab scale, small scale, and then weir is for the large scale. So this is the figure and schematic diagrams shows the notches and weirs. Okay, you in Bandar Seri Alam, you may found these types of notches, this type of notch or weirs in the lake in front of this Seri Alam police station. So in that lake, we found that the notch has been used to control the flow rate of water from the lake to the river, and it will flows that in order for the authorities to maintain amount of water in that lake, so they have to use that kinds of they have to use the notches. Then it blocks the water at a certain level. It will flows out like this, okay, and it will maintain at the same amount of water in that lake, okay. So in order for us to determine the area of the strip, here we refer to this figure. So the area of the strip is B, is a width, times with delta H, change of height. So delta H here is this area. So to find this area, we must times width times with length, okay. B times with delta H, we will get these kinds of area. And then the second one, velocity through the strip. So set to GH. The velocity through the strip is derived from this equation actually. So we have a free stream and then we have notch or weir at this point. So we want to find what is the velocity at this point. So we have water here flows through the notches, okay. So we will at this point we will apply the Bernoulli's equation. We know that at the free stream the velocity will maintain at 0 meter per second, and then that level will maintain that free surface will maintain at that level. So we will apply the Bernoulli's equation from this point to point number 2, where the point number 2 is located at the notches. So from here, we will apply the Bernoulli's equation directly. So P1 over rho G plus U1 square over 2G plus Z1 equal to P2 over rho G plus U2 square over 2G plus Z2. So from this point, we know that velocity at point 1 is 0 because it maintains at that level and does not reduce or increase. So therefore U1 will be at 0 meter per second. So for the pressure, pressure 1 and pressure 2 will have the same amount of pressure because it is open to atmospheric pressure. So point number 1 and point number 2 is atmospheric pressure, therefore P1 and P2 will be the same. So now we have only Z1 U2 square over 2G plus Z2. So rearrange the equation because our main focus is to find what is the velocity at 2. So U2 square over 2G equal to Z2 minus Z1. Now U2 is 2G, U2 square, Z2 minus Z1. So U2 is equal to Z2G Z2 minus Z1. Now we take a look at Z2 and Z1. If we take Z2 as our datum, so Z2 is for our datum, so 0 meter. And what about Z1? So Z1 is, as we can see here, Z1 is the H, okay, H, height. From here, this is the point where the water flows out. So this is the point number 2, and point number 1 is a free surface here. So we have H here, therefore Z1 is H, because Z1, the point number 1 is H meter above point number 2, therefore Z1 is H. Then we have to substitute into this equation. Sorry, no, I rearranged in the wrong direction. So this one is Z1 minus Z2. Sorry, Z1 minus Z2. Because here is Z1, Z2 will be moved to this side, and then Z1 minus Z2. It should be Z1 minus Z2. I'm really sorry. And then after that, we know that we already have identified Z2 as our datum, and then Z1 is H. Therefore, we substitute into this equation, so we will get U2 equal to Z2G. So Z1 is H minus 0. So therefore, we will get U2 is equivalent to 2 set to G H. So it is the same as this one. So velocity through the strip is set to G H. So what about discharge through strip? So discharge through strip is change of Q equal to area times velocity. The Q, the flow rate is always changed. Therefore, we have to use differential form. So del Q, delta Q. So change of Q. Q will be changed times to times. Therefore, it will have a differential form. So area times with velocity, we will get the discharge through the strip. So the area B delta H times with set to GH, we will get the velocity discharge through the strip. So from this equation, we will integrating from H equal to 0 at the surface to H equal to H. So here we have H. Capital letter H is head of the notch. So at the bottom of the notch to the free surface. So that is what H, capital H, represent. So for the Q, so we have here, so del Q, so del Q equal to beta B del H set to G H. Now, for this side, we will integrating it from H, from 0 to H. But for this side, for the Q, we will integrating it from 0 to Q. So therefore, when the result of integration will be this one. So Q equal to set to G, 0 to H, BH 1 over 2 DH. So this will integrate in terms of DH. Okay, this is the general theoretical discharge equation. So you will refer to this for this rectangular and V notch. So before the integration, okay, of equation 7.2 can be carried out, B must be expressed in terms of H. So from here, we will integrate for the rectangular and V notch. So let's take a look at the rectangular notch. For a rectangular weir, notch and weir is the same because weir is for the large scale and the notch is for the small scale. So for the rectangular weir, the width does not change with the depth. So there is no relationship between B and depth H. We have equation B, constant B, giving, so here this is the opening of the notch. This is not the notch itself. For example, if you go to the lab, we will have these kinds of dimensions of the rectangular notch. This is at this point, okay, at this side. Okay, we are not referring this to this one. Okay, we are referring to the opening of the notch. Therefore, the opening of the notch, we have head of the notch here, H, and then we have B, width of the notch here, so B. So from here, we will substitute the value of that B and H into the equation. So now, from here, we know that we have B, small case B, small letter B, then this B is actually width. So width for the rectangular notch is B, capital letter B. So B, substitute into this equation, B, capital letter B. And then what about H? Because we want to integrate H and H. Okay, so we will substitute H, capital letter H here. Okay, because we want to integrate from 0 to H. So from here, I will take a look at here, 0 to H, and then we want to integrate H half dH. So here we will integrate. So the integration product of this part is H 1 over 2 plus 1 divided by 1 over 2 plus 1. Okay, so from 0 to h. Therefore, we will get this the products of the derivations of this integration is h 3 over 2 divided by 3 over 2. So we will get 2 over 3 h 3 over 2. From here, we will substitute into this. So this integration product is this one, and then we substitute. Therefore, we will get that the equation to find theoretical discharge for the rectangular weirs is 2 over 3b sub 2gh 3 over 2. So you will use this equation to find what is theoretical discharge of rectangular weir. Okay, so now we move to V notch. So V notch derivation is a little bit different with a rectangular notch since we have V notch shape. So from V notch shape, we take a look at this figure. We know that V notch shape, we have theta here. So from here, we want to substitute the value of B. So from this general equation, so we have B, width of this of the notch. So to find width of this V notch, we have to divide the opening of this notch into 2. So we will apply the triangular equation to find what is the B here. So I divide this notch into 2. So therefore we have theta over 2 and theta over 2. When we added these two theta, we have theta. Okay, now our focus is on this A. I put it as A and A. So to find B, we have 2A. So 2A. Now I will find what is A. Okay. So at this point, we know that we will be given with the height. Okay. So this is h is the from here to here, the capital letter H, and then h is when that this is free surfaces, and then this is the bottom of the notch, and then when it flows through the V notch, what happens is the water will not discharge the water with the H, capital letter H, but there is some decrease and the flow of water will be reduced. Okay, the height of the water will be reduced here from the H here. So we have H, and then after it flows through the V notch, it will reduce, and we have H, small case as we have H here, reduce, and then we have to find what is the H of this. So to find here, from this point to this point, so we have these kinds of height. Okay, we have to determine what is the height of this. So to find this, we have to subtract H minus H, then we get this. Let's say I say this is T, for example. So to find T, we have to minus H with H, capital letter H with small case H. So we will get this height for the T, where the water flows through the nozzle, through the V notch. So to find what is the H, we have to apply the trigonometry equation. Okay, trigonometric equation. Sine theta T over H so from here we will use tan theta because we have this value. we want to find this, we have this value. Okay, we do not have this hypotenuse value. We do have this value, which is t, and then we want to find what is the value of a. So therefore, tan theta over 2, because here the degree is already been cut into half. So tan theta over 2 equal to, so we want to find what is a divided by, we have t here, h minus h. So to find a, tan theta over 2, okay, times with h minus h. We do have this equation. Okay, so to find what is b, width of this b naught, so we have to multiply with 2, because both of these width have both of this length a, both of these a have the same length. Okay, so b is equal to 2a. So we have to 2 multiplied with 2 for the tan theta over 2. Okay, h minus h. So therefore we get that b is actually tan theta over 2, okay, h minus h. So we already get the b value, b equation. So from this b equation, you have to substitute into v naught equation. Okay, so v naught equation, so we do have, not v naught equation, the general equation. This is general equation. So set 2g, okay, integration of 0 to h, and then b, h, half dh. So now we substitute this into general equation. So we will get that set 2g, so from 0 to h, b is 2 tan theta over 2, okay, h minus h, h 1 over 2 dh. So now we can move 2 tan theta over 2 to the outside of this integration, since this does not required for the integration. Okay, so we only integrate to the dh, we are not integrate tan. Okay, therefore so q equal to set 2g times with 2 tan theta over 2, so integrations of 0 to h, so h minus h, h 1 over 2 dh. So we already have that kinds of equation. Now we have to integrate this integration part. So q equal to, okay, set 2g times with 2 tan theta over 2. So I integrate that one. Oh, before integration, I have to expand that equation first. So to expand this equation, so 0 to h, then h times with h over 2, and then minus h 3 over 2 dh. So we integrate this equation. So 2g times 2 tan theta over 2. So from here, h 1 over 2 integrate dh, we will get h 3 over 2 over 3 over 2. Okay, and then minus 3 over 2 integrate, so we will get 5 over 2 over 5 over 2. Okay, so from H to 0. Then Q equal to sec to G times with 2 tan theta over 2. Okay, we have 2 over 3 H 3 over 2 minus 2 over 5 H 5 over 2. So H to 0. So the determinants of this equation is not the same, since then we cannot plus both of these equations. So therefore we substitute first the value of H into this equation for the H, small case H. And then when the 0 value has been substituted into this equation, it will be 0. Therefore, so Q equal to sec to G times with 2 tan theta over 2. So we will get 2 over 3 H 5 over 2 minus 2 over 5 H 5 over 2. Okay, we have the same 5 over 2, therefore we do not have the same determinants here. So therefore we have to make it same. So how? So I will multiply this. Okay. So then after I multiply, I will get that the value of that one is 1 theta over 2. Okay, I multiply that, we'll get 10 over 15 H 5 over 2. Okay, minus, right, minus, so we have 6 over 15. Okay, H 5 over 2. So after that, we do have 15 and 15, the same determinant, and then H is the same. Therefore, we have to minus 10 with 6. Okay, we get 4. So from here, Q, so we get sec to G 2 tan theta over 2. So we will get 4 over 15, okay, times with H 5 over 2. So now we have to multiply 4 with 2. So we will get that 8 over 15, okay, sec to G tan theta over 2 H 5 over 2. So this is the equation. I show you the derivations of the V notch, and then at the end of that derivation, we will know that the discharge rate of for the V notch is Q equal to 8 over 15 sec to G tan theta over 2 H 5 over 2. This is theoretical. Okay, theoretical discharge rate. So for you to get what is the actual value or the actual discharge of V notch or rectangular notch, as I mentioned before in the previous video, we have to multiply with coefficient of discharge to get the actual discharge. So Q actual times CD times with that theoretical discharge. Okay, from the previous equation, CD times with Q theoretical, then you will get Q actual. The same goes with the CD, so you have to times with Q theoretical. So this is when you calculate by using this formula, you are actually calculating the theoretical discharge. The same goes with this equation. This equation for rectangular weir, where we have Q equal to 2 over 3B set to GH 3 over 2. Okay, now I will explain what is H. The capital letter H is head over the notch. Okay, in the question, it will mention about the head over the notch. Or maybe they will give you the location of the notch from the bottom of the free stream of the open channel, and then it will give you the depth of the water. Then you have to calculate the head over the notch by subtracting depth of water with the location of the notch from the bottom of the channel. Okay, it's okay. That will be explained after this. Okay. Okay, now we take a look at this example. In an experiment of 90-degree V notch, the flow is collected in a 0.9 meter diameter vertical cylindrical tank. So we do have this V notch. So this is open channel, and then we have V notch here, 90-degree V notch, and then we have water that flows through the V notch and collected by this 0.9 meter vertical cylindrical tank. So this diameter is 0.9 meter. So it is found that the depth of water inside the cylindrical tank is increases by 0.685 meter. And the time taken for this height to achieve is 16.8 seconds. So to find when the head over the notch is 0.2, so the head over the notch is the capital letter H that required in your equation, okay, to determine the discharge of the notch. Now we have to find what is the coefficient of discharge. So since we collected the water from the notch, so the rate or the discharge of this water from the notch is considered as actual, because we know the height of the water and the time taken for the water to fill into the cylindrical tank. So that is the actual. We are not calculating it, and we are not assuming or expecting that the volume of water should be like that, should be that amount. But this is the real. We collected the water, and then that water flow rate is, or the volume flow rate is considered as actual. Then from here, we have to determine what is the volume of the water. So volume of the water, we know that to find the volume of this cylindrical tank, we have to multiply the area of the tank with height. So we know that the area, the diameter, the area is a cross-sectional area. So the diameter of the tank is 0.9. So we have to multiply pi with 0.9 squared. So it is in meter. If it is in centimeter, you have to convert it into the SI value, which is meter. So now the height of the water inside the cylindrical tank is 0.685 meter. So from here, you will get that the volume of this the volume of the water inside the tank is 1.743 meter cubic. Now from the volume, we can actually calculate the volumetric flow rate or discharge, the actual discharge, the discharge of this water. So because we already been given or we already been supplied with the info on how long does it takes for the water to fill to 0.685 meter. So now volume flow rate, volume flow or discharge rate, I will put it as Q. So we have to divide volume with time taken. So volume is 1.743 meter cubic divided by 16.8. So you will get that the volume flow rate of this water is actually 0.104 meter cube per second. So that is volumetric flow rate or discharge. This discharge represents the actual discharge because we collect that water coming from V0. Then what we have to do is we have to determine what is the coefficient of discharge. So by using the equation of the V0, so Q equal to CD 8/15 times with third to G times with tan theta over 2, okay, times with H 5/2. So substitute the value into this, all the values inside this equation. So you will rearrange this equation and find what is CD. So from here, your CD is 2.46. Okay. So here is theta. Theta is this is theta. So theta. So you please do not convert this theta into radian. This is degree, and sometimes the students confuse about this theta. They change it into radians. You cannot. You do not have to change these values, these degree values into radian. Put it as it is. Okay, 90 degree. Then you have to put it inside this as 90 degree. So what about the H? H is head over the notch. Here, the head over the notch is already been given 0.2. So you substitute into this equation and then rearrange to get what is CD. Q is already been calculated by you. Okay, this equation is Q actual. Okay, now we already know that this water coming from the V0 been collected by the cylindrical tank, and that Q is actually actual Q. Okay, so we get that we got the value of CD is 2.46. Okay, that is for example 1. Okay, very simple. We just plug in the values inside this equation and then you will get the value of whatever thing or parameters that you want to find. Now we move to this equation. So this is example 4. Actually, we have example 2 and 3. But I think that example is quite simple. And then we have to go to the example 4. Okay. So the flow rate of water in 5 meter wide horizontal open channel is being measured with 0.6 meter high sharp breasted rectangular weir. So at these flows use rectangular weirs. So you cannot use V0 equation to find what is Q. So you have to use rectangular equation to find Q. Okay, the water depth is 1.5 meter. So you already been given with the info of the depth of water. So the depth of water is about 1.5 meter. Okay, and the discharge coefficient, so CD given is 0.7. So you have to calculate the volume flow rate and velocity of water. So directly use, okay, because here we already been given with CD, then this question is actually want us to find what is the volume flow rate in for actual volume flow rate or actual discharge, because CD is already been given. If in the question that does not give these values, CD values, then you may calculate volume flow rate for theoretical. Then here we have to find what is the Q actual for the rectangular notch. So Q actual is CD times with 2/3, okay, B set to G H 3/2. So B width of this rectangular is already been given 5 meter. What about H? Head over the notch. In this question, give us the depth of water and does not give us about the head over the notch. what we have to do, we have to refer to this figure. So we already have the depth of water. And at the same time, this question also gives us 0.6 meter, where the locations of the head of the notch is 0.6 meter from the channel bottom, okay, or bottom of the channel. The locations of the notch to the bottom of the channel is 0.6 meter. So head is actually this, head over the notch, h. So to find h, we have to minus 1.5 with 0.6 meter. So h is actually 1.6 minus 0.6. So you will get that your h is actually 1 meter. Substitute into this equation. CD is 0.7, B is 5 meter, 2G is 9.81, then you will get that the Q actual is actually 9.3 meter cube per second. So you already saw for the volume flow rate. So what about the velocity of water? So velocity of water, as I showed before, we will use set to G h. So this h is actually h, head over the notch, h. So you have to substitute to g h with 1. And then 2 times with 9.81 times with 1. So set answer, you will get 4.42. So this will give you 4.43 meter per second for the velocity at the notch. So notch. Now we do not know whether that velocity is for the notch or for the upstream. We have two different velocity. One is here, is upstream velocity, and 2 is downstream velocity. Which velocity that we want? So therefore, I suggest that you will find both of these velocity. So to find velocity at 1, we already found the velocity, already calculated the velocity at point 2. Now we calculate the velocity at point 1. So for the velocity at point 1, we will use Q equal to UA. So U equal to Q over A. So what about the area? Area is 1.5 times width, 5 meter width. Because if we can see from the front, we will see these kinds of area, these kinds of shape. This is 5 meter, and then this is 1.5 meter. So multiply 5 times with 1.5, you will get 7.5 meters squared. So Q that we get from this equation is 9.3. So divide by 7.5, you will get the velocity of the upstream velocity is 1.24 meter per second. So because the question does not specify at which location of the velocity of water that this equation wants, therefore you have to find both of these equations, upstream velocity and downstream velocity. So that's all for the chapter 7, notch and weirs. Thank you.